Hello, in this video we present a demo of a network slicing prototype that has been developed on the top of a Cloud RAN architecture provided by OpenAir interface. The main components of our prototype are depicted in this figure. We have a remote radio unit, a remote radio cloud unit, and a core network that is implemented in a virtual machine. The latest component of our prototype is an SDN controller that is based on the software provided by the FlexRAN project. More specifically, the remote radio unit consists of a Netus USRP B2100 card, which is connected to the Ubuntu desktop computer via an USB 3.0 interface. The remote radio unit is then connected to the RRC by means of an Ethernet fronthaul. It is worth to note that the fronthaul connection between the remote radio unit and the remote cloud center unit is performed by means of the F4P5 splitting interface that is provided by OAU. Our prototype is then completed by two smartphones, in the most specifically a Samsung Galaxy S6 and a Samsung Galaxy Note 4, which has as co-user. So in this moment we can see that these users are connected with Open Interface Operator by means of a 4G connection. Let us now focus on presenting the slicing solution that we have developed in the SDN architecture. Differently from the legacy scheduler approach that are used in LTE, in our prototype we implemented a particular scheduler that let multiple virtual operator of over-the-top service provider to have access to the portion of the spectrum in an isolated manner. More specifically, we have developed an SDN northbound interface that interact with the controller provided by the FlexRAN project, and this northbound interface give to the user of our prototype the possibility to configure the size of each slice on demand and in real time. In this experiment, we assume to have two slices. In particular, the smartphone on the left belongs to the slice 0 and the smartphone on the right belongs to the slice 1. In this experiment, we want to prove that our prototype will respond well to the configuration command that come from the SDN northbound application. This means that we expect that the smartphone that belongs to the slice 0 has much better performance than the smartphone that belongs to the slice 1 because of the currently size of the slice that has been decided by the northbound app. And in fact, as we can see in the video, the average throughput of the slice 0 is almost 1.7 megabytes per second, while the average throughput for slice 1 is less, almost 400 kilobits per second. An important characteristic of slice that we want also to demonstrate is the isolation property. In fact, any variation on the traffic in the slice 1 does not affect the performance in the slice 0. As we can see, the throughput remains almost constant in the slice 0. We do now another experiment to validate the capability of our testbed to change the size of the slice on demand during the real-time execution of our emulation. We change the size of the slice 0 from 8% to 6% of resource block, while the size of slice 1 is changed from 20% to 40%. As we expected, the performance of user that belongs to the slice 1 are improved compared to the previous experiment. This means that our testbed is capable to react to the input of our node-bound application even in real time and during the emulation that we perform. This is our current work on network slicing. We aim at implementing more complex slicing algorithm that we will validate in our future demo. Thanks for watching.